I know it. I know it.
Where are you going to present from?
Right about here. All right, guys, we are officially live. Everything you're saying and doing is being heard on YouTube.
Woohoo!
To our mini follower.
Burn it down.
Yeah. So this is the time to have some really hot political takes. I appreciate, this is a really good turnout for us in person. We've had turnouts bigger, but I mean, not in a while. We've been kind of training, so this is fantastic. So thank you all for being here. I think we have some new faces. I convinced some people to come in. Other people found us on LinkedIn and I think felt obligated because they're involved with the Boyd Innovation Center. We have some new faces. So thank you all for being here. For those of you who don't know, this is Silicon Swamp. We try and do this weekly-ish. I know I've had a bad streak recently. I will try and be better when I can. So for those of you who don't know, we try and do these. Now we do a lot of these online, and then we try and have as many in person as we can, especially when I'm in town, because I split time between SF and Columbia. But if you have any questions or you want to give a presentation, which we would love to have, please come talk to me. You can talk about anything, as long as it's somewhat technical. It can be what you do for work. We love when people talk about their hobbies. It can be what you studied in school, a project you did, or just something you read that you want to share that you have some knowledge about. So if there's anything that you're really passionate about, and we'd love to have you come talk from all sorts of different varieties of experience ranges, right? I think a lot of people see this and they're kind of intimidated, they don't think they know enough. I think it's really cool for people that are kind of newer to their technical education to actually do this stuff earlier and learn and get feedback, and we're happy to give it. So, we continue to enjoy the Boyd Innovation Center for hosting us here. But when we're not here, we send out online links, and we'll try and keep trying to do this as close to weekly as we can. And I'll just cop up. I don't have anybody for next week, so next week we're on hiatus, but I'm working on it. So we've got some people lined up. I'm just trying to get the schedules. So if you want to speak, like I said, come find me. I'd love to put you on the schedule. So without further ado, what everybody's here for, we're going to talk today about one of my favorite subjects, which is swarm intelligence. Who here knows what swarm intelligence is? Awesome. That means that this will go well for me because nobody can tell me if I'm wrong. All of you that are currently on Wikipedia fact-checking this, please stop. So what we'll talk about today is something I learned about when I was in grad school. I'd never heard of it. I went to graduate school. One of the gentlemen that will be in this presentation was the guy who invented the term. Actually was a professor who taught me there. And it is now highly involved in what I do for work, for my company, Collide Technology. And so I'm very passionate about this. I think it's a really interesting, unique aspect of what I would consider artificial intelligence, but it's a type of artificial intelligence that people have not really seen before. One of these will change a slide. It's that one. That's our agenda. Cool, nobody can read it. What is a swarm intelligence? Swarm intelligence is a group of nature-inspired, or what we would call biomimetic algorithms. What we looked at in nature was that there's certain things that animals and groups of animals can do, and they do really, really well, but it wasn't necessarily well understood how they do it. So a really good example is flocking behavior. Like, how do birds, you see hundreds of them flying around, and they very rarely run into each other, right? But they can change direction very quickly. They can do complex patterns. So they do this, and they do this all somehow without really verbally communicating. There isn't one bird in charge. We also see it in a lot of other nature-inspired solutions, like how do bacteria organize? How does mold grow? How do ants build complicated structures? And so in the 80s, this was a problem that people originally were trying to solve in the field of robotics. And a great metaphor for like the kind of problem you might ask yourself for swarm intelligence is, let's imagine you have 100 children in a playground. And you say, look, we've hidden some cookies, right? How would you coordinate all the children to go find cookies? And the answer is probably not well. And almost every plan you would have like a central person to it, right? You know, you'd say, okay, go talk to Mark. Mark is going to tell you to search this area, and when you're done, you come back. But what if there is no Mark? And remember, these are children, so they're not going to do any of that, right? So how would you coordinate? So a huge thing that we have to ask ourselves, and this is where it diverges from like traditional AI, is how do you coordinate a bunch of agents with no central coordination, right? So if you've got things like ants, children, right? You couldn't give complicated instructions to any of them. None of them are that smart, so they're not going to kind of figure it out. They're not loud, they can't communicate across the room, so you can't have good group coordination. And this diverges highly from how we do AI. For those of you uninitiated, if you've ever trained an AI model, what you do is you take a bunch of right answers, you let the AI guess, and when it's wrong, you tell it how much it's wrong by. And you keep doing this until the AI is pretty consistently correct. But you have to know the right answer. So what if you go into an environment where we don't know the right answer? Like you have to search a field, we don't know where the cookies are, we don't know how many cookies there could be. How would you come up with an algorithm that would solve this? So the definition of swarm intelligence is essentially the collective behavior of decentralized, self-organized systems. It comes from Benny and Wong in 1989. Gerardo Benny was the professor that I was the teaching assistant for. He was my favorite professor in college from the classes I took. Really cool guy. But this definition encapsulates this sort of system that we didn't understand. And in Gerardo's case, he meant even outside of the field of computer science. While he worked in robotics, he was a physicist. He meant we don't even understand how animals do this. And back in 1989, so he was describing that we needed to understand how swarms of groups within nature work, whether we can replicate them for computers or not, right? And that was a huge problem. When I met him, he was still very much teaching on what I would call like the philosophy of intelligent systems, right? And he had like a definition of intelligence and what that meant. And you spent basically a 12-week class with him slowly defining intelligence, and he would like add a word each week. And then we would talk about why that was important, and then we'd go back to class, and like by the end of the class, we had this like 2-sentence long definition for what he thought intelligence was. And it was eye-opening. So there's some essential key traits. Decentralization, so no single agent can know what the answer should be. Like no single agent can know where all the cookies are, right? You can allow local interactions among agents. Like I can talk to Mark, I can talk to Jay, I'm not going to talk to George. So I can talk locally to people, but one of the things is you can't do what I'm doing right now. I can't talk to everyone, right? I'm not allowed in these systems to be like, hey everyone, we're going to go over here first. So take that out of the equation. And you want to have simple rules because each agent has to be what I always call dumb, right? Each little individual ant's dumb. Has like 12 neurons. It basically just sort of twitches around in the right direction its whole life and then dies. And naturally a characteristic is these things are highly resistant to failure. I mean, think about how many ants you would have to kill individually before you killed an entire like anthill. You just couldn't do it. I mean, you could sit here stomping all day and ants will still be there, highly resistant. There are tons of really good examples. We're going to dive into these today because they're all really fun for those of you who like that sort of thing. So there's ant colonies and how they optimize and find food, foraging paths. Bee swarms efficiently communicate through dances. They have a really cool local dance protocol. Fish schools and bird flocks navigate without bumping into each other, all very fluidly. And all of these have been studied both from the biological side as well as like how you can implement aspects of these to solve really cool problems. From an engineering perspective, you're sort of looking at like many minds, even bad ones, are better than one. And so you get these highly resilient systems and you get a group of simple agents that outperform simple, more complex agents. A great example is if I asked us to very quickly like build a bridge, it would be difficult, but ants will do it naturally, right? We would sit here, we would, well, Mark, what do you think of? Like, oh, George, so you got a civil engineering background. Cool, 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 cool. So what do we think? It would actually be harder for us in some instances to do some of the complex behavior that we see emerging. Now, the reason I thought this was cool was because I was always really interested in what we call emergent technology, like technology that sort of emerges from like systems that have basically no inherent definition. And so, for those of you who don't know, the thing I studied in college was nanomagnetics, right? I worked for a guy who was like famous in the hard drive industry, and to me that was the reason I studied it, right? Because you have essentially a bunch of molecules sitting around, and for some reason they will just spontaneously start coordinating, and then it will become magnetic, and they'll make magnetic domains. And I found this fascinating. And so when I first was exposed to this, I just thought this is like the coolest thing ever. Like, why doesn't everybody research this? So the historical roots. In about 1989, Gerardo Bini and Jing Wang, they published pioneering research on cellular robotic systems. Originally, these were robotics guys. They were like, oh, what if we could build robots that could fly around like birds, right? Very like 1989, like sci-fi idea for like where technology would head. But they came up with some definition of like what that would mean, and that became the predominant definition. In 1992, somebody comes out with an algorithm called ant colony optimization. So we know how ants work, and I'll talk about it specifically, but somebody actually replicated it in a computer, and what they found out was that it solved really complex problems very, very quickly. To give you an idea of the kinds of problems it can solve, I should have thrown a slide up, and I apologize I didn't. There's a classic problem called the traveling salesman problem. The traveling salesman problem it's a classic. It's just one thing. If I was a salesman and I had to travel to, say, 15 different cities, and I don't want to repeat any city, what is the shortest route I can take? Well, if I asked you to do that for 5 cities, you can do it on paper. If I asked you to do it for 10, it'd take you a little bit of time, but you can figure it out. If I asked you to do this for 20 cities, it would be incredibly difficult. It would take a very long time. You can see how, even though I haven't drastically increased the number, I went from 5 to 20, the problem gets exponentially harder and harder. These types of problems, there's a mathematical term for them called NP-complete, non-polynomial time. What that's to say is that as you add more entities, the solutions get drastically harder and harder. It's a huge problem in computing, and so those of you who study computer science, you run into these problems all the time. The traveling salesman problem. How many things of which size can fit in a bag? That's an NP-complete problem. What is the shortest route between a variety of locations? NP-complete. I want you to order $13.12 from this menu. NP-complete. All these problems you can figure out could be solved, but they're difficult. They're problems that people are bad at and computers are really bad at. So normally what we see is when we run into these NP-complete problems, they become a huge issue. What we found with ant colony optimization is it doesn't solve these problems, but it approximates them pretty well. And in a lot of real world scenarios, like let's say you're a traveling salesman, you want to find the shortest route. Let's say you find the 3rd shortest route. It's still better than what you probably would have come up with yourself, and it happened really quickly. It's good enough, right? So there's really good, and this changed my world. When I first studied AI, I was in a program at University of Central Florida where they had professors that were teaching us about AI, and one day a guy gave a presentation. He's now, I think he's the head of AI for Uber. Like he went on to have like a really cool career. When I was a big fan of him because I had actually read his original paper. He had invented an algorithm called NEAT, Neuro-Evolving Augmenting Topologies. Now, you might think, wow, I mean, I'm sure this is what you're all thinking. Wow, Fred, you must have been a really smart undergrad. You were reading papers. And boy, that just the whole package, like really smart, good looking, doing all the work. But the reason I'd actually read his paper is because he had turned it into a video game. And I had played the video game. So he had created this algorithm. Everybody told him the algorithm was dumb. And so he had created a game called Nero that used that algorithm to program the entities. And I had, for whatever reason, I've been like the only student in that program that had played the video game. So I found this guy fascinating. And his first presentation to us, he was saying, oh, we're trying to solve this image problem. And it turns out to be NP complete. And I thought the next thing he was going to say was, and so we had to stop. And then he goes, but that's essentially a solved problem. And then he like went on to the next slide. And I was like, well, wait, hey, what do you mean NP complete, solved problem? For those of you who don't know, that's a class of problem for which there's $1 million prize for, right? If you can solve NP complete, there's an organization that will give you $1 million because nobody has ever solved generally how to do it. And I said, what do you mean this is a solved problem? I didn't get that memo. It's a famous mathematical problem. He goes, oh, you're right, let me clarify. There are very many good approximations that in the real world are good enough. And that they're very efficient. And then he went on. And that stuck with me. That stuck with me my whole career. So by 1995, we get a thing called particle swarm optimization. It draws inspiration from the behaviors of fish, as well as swarms that grow in size, right? Things that merge together. And I'm going to go through the details of some of these. And and all of these kind of, we're kind of like jumping around here on stuff, come from an original Boyd's model, which was a simulation that they originally did with 2D structures, trying to figure out how birds flock. So a lot of this starts in the 80s, has kind of a peak in the 90s, and then just sort of dies out, right? So what are some of these emergent things that we study? Well, for one is termite mounds. Termites, obviously not very smart, but they build large complex structures. Next, starling myrmitations. So this is the flocking behavior of birds. We've already talked about ants, but specifically there was also a lot of study in ant bridges. Like how do ants figure out how to coordinate to build structures of themselves to get over water and navigate obstacles efficiently. Ants don't have a language per se, right? They can't coordinate like, okay, I'm going to stand here and you're going to stand on my shoulders. So how are they able to figure out? And then how do they know that like if you're an ant and you're this small, how do you even know how far the bridge has to go? Right? So you actually know, like the goal is to get over the water, but I actually don't know where the other side of the water is. So I have to coordinate somehow to build a structure that can span maybe a quite large distance of an unknown value. I want you to think about that as an engineering problem, even with people. If I said, look, we're going to build a bridge, but I don't know to where. And you'd be like, oh, okay, so we're going to Alaska. Cool. So we're going to build this bridge to nowhere, and how far does it go? And it would be hard to figure anything out. But ants do this all the time. And finally, even slime mold networks. So slime mold, I'll show you some cool pictures of these. Mold is able to find consistently the shortest pathways between densities of nutrients. And so well that they've actually been used to solve complex transportation problems, like in real life.
There's a thing in Japan, sorry to interrupt.
That's literally, yeah. We're gonna, I was like, some of you have probably heard about the Japanese train system. So why is this important? And this is like why I think it's important. Traditional approaches are typically centralized. If you train a typical AI, you train one neural network on one computer, right? You may disperse it across many computers, but essentially all the weights end up in one spot, which means you have a single centralized failure point. Also, if you have a computer network that's running an AI, if you bash the computer, that's it, your whole network's down. Whereas, theoretically, with a swarm, if I had a swarm of Raspberry Pis that could all work together, I could just like start like baseball batting, like 30 of them, and the swarm would just keep going. So no vulnerability to single approaches. It's limited adaptability to rapid environmental changes. So if you look at a training an AI, hey buddy. Everybody wave at Jay. Because just want him to feel welcome. Happy to see you. So as things change in your environment with traditional AI, you have to retrain the model, and you may have to put in new elements, and you have to retrain it and then hope that you account. Swarms should be adaptable. They rely on comprehensive data gathering, and this is an important part. A lot of the work that I do, especially in big factories, people don't know the answer yet. They haven't trained it, they haven't collected the data. So the question I'm always trying to solve in data science, both for factories and in other systems, is how do you solve a problem where you don't know what the right answer is, right? And that's a really different thing from a traditional approach. So the swarm approach allows for us to be decentralized, robust, and not necessarily need any or a lot of upfront data. Completely different than traditional AI, like in deep learning techniques. How am I doing on time? All right. So these are our key things. Metaheuristic, common structure, biological inspiration. Then we have a biological inspiration. We have the key algorithm families that we're going to talk about today, which is ACO, PSO, and some artificial dequantization. Now, the reason I mention this is algorithms for deep learning are highly general. So most AI algorithms can be applied to many, many different problems. Swarm intelligence algorithms are not, right? Because they're usually mimicking some function of an animal. So they usually have to be matched to the problem that you're solving. So ant colony optimization is amazing for pathfinding. Particle swarm optimization is great for continuous optimization problems, like if you have multiple machines running and your balance loads. If you have resource allocation, artificial. And you have to know that, which is not necessarily true. Like in general, I may need to know for traditional AI, I may need to think about like how big of a network I need or how to accommodate different resources. If I'm doing traditional machine learning, I might have to kind of worry about what models I use depending on the type of data. Like if I have, structured or unstructured data, whether I have numerical data or categorical data, that might affect my decision. But in general, the models are relatively general. Whereas here they are not. They're very, very, very specific. And the field has largely evolved quickly from the 80s until the 2000s, and it encompassed a huge area of both computer science and for a long time robotics. There was a ton of like swarm robotic research up until like 2006. And then unfortunately it kind of like died out. It's the same slide again. Okay. So the key algorithm that you'll probably see people talk about swarm intelligence for the most is particle swarm optimization. I think that's because this algorithm is very good, and also it has swarm in the title. So normally when I say swarm optimization or swarm intelligence, people are like, oh, you mean like PSO? Yes, you picked the one that has the same words in it, and you were correct. This is a very strong swarm intelligence. PSO is inspired by social dynamics that are diverse and efficient. So what you do is, let's say you want to figure out where on a curve the highest and lowest points are, but I can't see the whole curve. What I would do is I would drop a lot of particles. Each particle will start moving, and it will adjust its velocity based on the slope. And so you basically can imagine that these particles are essentially like whizzing through the environment. And what you want to say is like, what's the highest point? Well, the highest point will largely be wherever something's velocity is almost zero, right? Because it'll be level. So you can imagine if you have a hill, you have a bunch of these like beads, and they can move up and down the hill, but it's dependent on how steep the hill is. At the top of the hill, they won't move at all, right? They'll bounce. And they can talk always to their neighbor. So I can ask Jay how fast he's moving, but I can't ask George how fast he's moving. And from this, what we can do is we take the velocity of each one, we take the entire velocity of the whole thing, and then we basically find which particle is moving either the slowest or the fastest. And that'll either give us the steepest slope or the flattest. So if you're looking in a terrain and you say, like, look, wait, what's the highest mountain in this map? You can put out these particles, and they'll start whizzing around. And these are all, look at the slope, calculated gravity. This is how fast I'm moving. Each one of those calculations is incredibly efficient. It's something a computer can do thousands of iterations of every second. So you can have thousands of particles doing these calculations over and over and over again. And especially with modern GPUs, you can do millions of these. And they'll eventually settle into a place where they're either moving very fast or they're moving very slow. And then we're able to essentially, by putting so many of them out, we're able to search huge spaces. Now, what I've described is something very physical. Like let's say you had a map and you wanted to represent that in a computer. But you can also do the same thing with data. Let's say I have a bunch of unsorted data in a database, and I want to find the maximum value. Well, I could try and say, like, we'll sort the database and I'll run through each element, but then I'd have to physically kind of run and bubble sort or do one of the others. I don't know, you computer science nerds know the other stuff. One of the other search algorithms. PSO can go through a huge database, and even in multiple dimensions, where this becomes really interesting. Find those solutions, or find pretty good approximations to those solutions. Very, very good. So that's where this starts to shine. Like if you just have one line of data, you can just sort it like normal. But what if you have data that has 12, 15 dimensions on it, right? Because you have a large feature space. How do you find a relative local maximum or minimum? PSO, right? And these become very efficient as you start optimizing for large dimensional spaces. So I'll give you an example for us, like what we use it for at our company. Let's say that we have a marketing client. The marketing client wants to have an optimized ad. Now, the problem with that is that that's not a static problem. Culture, information, the way we use technology and absorb it's constantly changing. And I mean like almost the hour. How people feel about things is happening all the time. Now, the things that affect that might be news sources, how words are being, what got posted on Twitter recently, what the sentiment is around certain topics. So if I'm running ads, I have all these dimensions. The time that I place the ad, the words that I use in the ads, how people feel about those words right now, how much those words cost, because you do keyword search, and so that's, all of that needs to be optimized almost continuously. So when we're doing this, we can use something like particle swarm optimization. I just gave you an example of 5 dimensions, right? And what it'll do is have these agents essentially running around, looking at all these variables, and then trying to find what the best combination is. And by being able to talk to its partners very quickly and efficiently, it can do this with very little computing power. Most of these algorithms will run fine on like my laptop. And this is 2017, nothing runs fine on my laptop. So you're able to get these really efficient algorithms that you can use to find highly dimensional spaces that are dynamic. And particle swarm optimization, great for that. Questions?
It might be a dumb question.
Great, good. I might have a good answer then.
Have you ever tried it on, maybe a little too technical too, have you ever tried it on optimizing a neural network against like Adam optimization?
I have not. Other people definitely have. Okay. There's like a ton of papers on this, right? Okay. The problem is that, first, Adam's real good for what it's for. The other problem is that like PSO sort of tries to assume that that at least some of your elements have a relationship to each other. Whereas within a neural network, they're all independent variables essentially that you're then weighting to each other, but they're not inherently tied. Like there isn't like, this thing's only connected because we changed the weight to it. And so you're trying to discover the right connection, but there's an assumption that essentially when you first start that your weights are random, and PSO kind of struggles with that sort of thing to be as efficient as Adams. But you can definitely do it. There are papers for guys that have done it. And there are systems, especially, you'll see things like trying to tune things that have like a recurrent layer added to them, where it does have an advantage. As I recall, I've seen some papers. And so yes, you can use this for a neural net. People do. Typically though, Adams, for what it does, is just so efficient as an optimizer, hard to beat. But and to an extent, Adams is, one could call Adams because it's highly related to a greedy hill climb, as a similar method. Like you're trying to find the greatest descent, right? The gradient descent that's the largest. And Adams is just solely that. Whereas the problem that Adams might fail at is when you've converged, right? Which is why you can frequently overtrain networks. Whereas PSO has, while not as efficient as Adams, is a little bit more robust against overtraining if you try and use it for stuff. So that's your trade-off, but most people can be like, well, I'll just tell it to stop when I get to 97%. So why would I use a heavier algorithm? But yeah, there is a bunch of research on this. Actually, probably almost every single one of these algorithms, some academic has tried to train a neural network with and use that as the optimizer. So you can actually go and find papers. I haven't tried it personally because it's not what I do. Like I'm not trying to reinvent the neural net. Not anymore. Yeah. Did that answer the question kind of? Artificial bee colony. So artificial bee colony works by inspiring the foraging behavior of honeybees, where worker bees search for food sources and they communicate by waggle dancing. At this point in time, if anybody would like to demonstrate a waggle dance, I would allow it. Any takers? Okay, no. All right. I'll let you guys use your imagination. So bees use a little waggle. So the algorithm roles, it divides bees into three main roles: employed. So they're looking for things that we know have known sources of food. Allocating resource, onlooker bees, which are based on the employed bees information, and then scout bees. The reason this is important is that there's a huge problem in computer science where you're trying to find new information, but you don't necessarily want to forget about old information. So what we talk a lot about is exploratory search in computer science, right? If you go into a new environment, how do you find like the best resources and then allocate to those resources? So this, because they have different roles, does this really well, because you establish that these are the resources where some resources will be allocated. So you can imagine if, I always think of that these things really as like physical things because this is how we do it, but if you had a warehouse and you want to consistently be able to pull from the right part of the warehouse based on which items. Once you find different places where common items are clustered in the warehouse, you want to keep sending people to that part of the warehouse. But there might be other parts of the warehouse that have cool things in it. So you might say like, okay, you three are gonna go explore and find new things in this warehouse where we might be able to find other packages we can pull from. And then in between, there will basically be these communication workers that are like, you come back and tell them, I found this, and then they judge whether that's good enough to start allocating permanent employees to, right? In computer science, I actually don't, I assume you could do something like, oh, I have 1,000 GPUs. I'm sure there's some sort of boring optimization problem that you'd use it for in computer science, but in real world, it actually gets used in warehouse management. So guys like Amazon use it to try and figure out where they should try and station employees while they're in between tasks. Like, oh, you should wait here because you're more likely to get a pickup from this area. So it uses a probabilistic model. It's a neighborhood search, and it allows you to also give up on resources that are bad. That's another common problem with a lot of fixed algorithms. It's like, oh, what if, let's say you're drilling oil. You're not going to be able to drill oil forever. Eventually, this spot will run out. Well, you can't just keep allocating resources to that. These sorts of algorithms account for that and would reallocate the resources on the fly. So it's been used for a bunch of stuff. Engineering design problems, I've actually seen some guys talk about using it for that, where you're trying to balance different function across a large service. I've never seen it used for training classifiers, but I do think that relates to your last question that, yes, somebody has done it, and maybe it's really good for certain types of classifiers because you're allocating aspects of the neural network to different multi-classification problems. All right, I've included this one, and I don't know a lot about it, right? So you're gonna have to deal with me on this one. I included it because the Firefly is our logo. I've never heard of the Firefly algorithm. I found it while I was getting ready for this presentation. So if you're like an expert at this and like you did your dissertation on it, just interrupt and you're on deck. You can talk about it. But I'm gonna mull through it. Fireflies have a really cool swarm behavior in that fireflies group together based on which firefly is the brightest. So here, as many of you know, the Congaree National Forest is famous for its fireflies that tend to synchronize. And apparently, the thing fireflies will do, because the way that they communicate to their local network is by broadcasting via light, and then the ones that see that as the brightest will tend to communicate and move towards it, right? So the farther a firefly is away, though, the dimmer it will look, which means that they'll start to collect in little pockets. And so if you see fireflies flying around, they're not just one kind of homogeneous mass, they're kind of in pockets. It'll be like a group over here, it'll be like a group over here. And that's actually a very interesting swarm behavior because other flocking animals don't do that, right? They usually try and take the whole group and put it together. So when you see a school of fish, you don't see pocket of fish, pocket of fish, pocket of fish, pocket of fish. But you do see pocket of firefly, pocket of firefly, pocket of firefly. So where you can use this apparently is like antenna design. People have used it, where you are able to figure out like the optimal routing by looking at where the electromagnetic discourse happens. So when you're trying to figure out how the current should run through an antenna, you're able to see how it distributes through the wire and creates electromagnetic radiation, and you can use fireflies to better allocate resources into those pockets. So like as you route around it, what you want to see is that you don't form very many pockets. Now where that shows up in things like nature is fireflies tend to group together, and then they tend to group together around a food source. So one firefly that's bright finds food, then they all find food. And that's how this is supposed to work. But feature selection, so you can use it in machine learning. Why? Because if any of you have ever used something like a random forest, you're trying to grab features. What's interesting about a random forest, though, in AI, is that we're typically looking at one feature at a time. But actually, a lot of features are connected. So when you look at something like XGBoost or something, it's actually using weighted nodes to try and explain how that there's some of the features have different connections between them. And that's why it can be a slightly more robust model. But you could also use Firefly optimization and still group certain features together and then even more narrow down and say these features are somewhat redundant. I think I have another slide on Boyd, so we'll get to that when we get to it. All right, ants. I'm gonna talk about ants. I use this one at work. It's one of my favorites. It's really cool. It's easy to understand. It's probably the first algorithm I learned about. Ants are really, really good at finding where food is. And they almost pretty well find really good optimizations. And what I mean by that is, if you look at, there's a ton of ants, 10,000 of them, and they're coming out of the anthill. The path that they will take to food will generally be the shortest, but I don't mean shortest by always like straight line distance. I mean shortest by the least amount of energy required to go collect the food and bring it back. But no ant knows where the food is. That's why they have to go find it. But they always end up forming these little lines that are highly, highly efficient lines. So how do they do it? The ant doesn't know it. The other ant can't go back and be like, oh, okay, Jay, see what happened is you go right at the leaf, and then when you see the pine straw, you're gonna just keep going, and then when you hit the road, stop for a second, and then go left. That's where the thing is. Go grab a piece of that and bring it back and tell Bob, right? They obviously can't do that, so how do they coordinate without that level of communication? And what they do is they actually drop a pheromone. They drop a little chemical while they're moving. They're always dropping this chemical. Now what happens is that chemical, it evaporates. It doesn't last very long. So when an ant finds something, it immediately follows its own pheromone trail back. The shorter the trail, the less time this chemical has to evaporate. And as other ants are moving around, they'll find, oh, and another ant was here, and there's a strong pheromone trail. I'll follow it. The shorter that trail, the more likely more ants will follow it. And the more ants that follow it, the stronger those pheromones will get, until eventually you have all the ants essentially following one line. Now, so that's called ant colony optimization. You can use it for pathfinding. So if you have a traveling salesman problem and you want to find it, what you do is you spend a bunch of ants on all the different sales paths, and they all move around, and the shortest one will tend to be the one with the strongest digital pheromone. This is incredibly efficient. Like what I'm describing, I mean, it's just sort of a biomimetic pattern, but computationally, the way you set these up, it's really computationally efficient. It runs really, really, really fast. So when you're trying to solve what were now very difficult NP-complete problems, you can now solve these in seconds and get really good approximations using ant colony optimization. And so pathfinding is big. We actually see some aspects of this algorithm get used in things like driving. So when you see these self-driving cars, it might look through, oh, I have to go around this corner and then I have to go here. It'll actually sometimes use an algorithm like this. So this is like one of my favorites because it's really visual. It's historically relevant. It's one of the first algorithms that came out. You can go online and we're not going to do it. I didn't want this to get overly technical, but you can like look up how to do one of these. There are packages that do it, and you can have a lot of fun with it if that's what you're into. I thought we had a Boyd singing here. The original swarm intelligence algorithm before we even had a name for it was a thing called Boyd's. It was created by Craig Reynolds in 1986. It's based on flocking behavior of birds. And the result from Boyd's is that you basically have a group of rules that are just separation, alignment, and cohesion. So separation is how far apart everything's supposed to be. Alignment is how well each element follows the same direction. And cohesion is essentially how well the group is doing that together. But it's only 3 parameters. And you adjust these 3 parameters, and you find that that's really all you need to get very similar flocking behaviors of birds. So you can take lots of these little, they call them Boyds. And you can get these very realistic group motions. Originally they were done in 2D, you can now do them in 3D. Why does this matter? This is still heavily used in video games. When you see items move through video games, a lot of them are still using the Boyd's algorithm from 1986, especially if there's like groups of them. So anytime you see one of these, like, oh, I was watching Lord of the Rings and there was this animation and there was like 100,000 people running through a field, Boyd's. It's always like it's this algorithm you haven't really heard of because it only exists in this kind of esoteric world. But if you're in like computer games and animation, it's this old algorithm that comes up all the time and that we experience all the time. And it's a swarm intelligence algorithm, right? There's just simple rules. No individual Boyd knows what's really going on. It just knows its relationship to its neighbors. But it's actually an algorithm that you have seen in your real life on television, on movies, video games. It's used a lot for like animation of like fluid flow, right? Because you can change these cohesion properties so that they start to fall apart, and that's how you can get water to look like it's like water falling off an edge. You'll see this for like wind, moving grass. So it's kind of an interesting thing. You've never realized that you've seen a swarm intelligence algorithm, but you see it almost every day in ads and stuff. It's really cool algorithm. It's one of the ones I learned about later, but it's one of the ones I think is really cool because, yeah, it's one that people have actually experienced. Whereas when I talk about pathfinding, it's like, well, I can picture it, that's really cool, but yeah, but how does that affect your life? And it's like, well, it's baked into some product that you might have used. Maybe this you've seen, and so it's kind of fun. Kind of a classic that we'll talk about, and Jay was already getting at it. Sorry. No, man, it's good. It's just, slime mold. So we found out in 2000, researchers in Tokyo, what we found out was that mold will grow little tendrils that is very efficient at finding shortest paths to its food source. So if you put like sugar water, a nice little path. So researchers at Tokyo actually did this in 2000. Like this isn't even a computer experiment. What they actually did was they took the Tokyo subway network and they wanted to figure out the most efficient pathways. So what they did was they took all the cities or the places that the stops would have to happen, and they put sugar water there. And then the mold grew, and it created a map. And you can actually get this. This was done in 2000. This was actually used in a real-world civil engineering project. In 2007, they used it to solve mazes. You can watch videos of this. In 2010, people started developing algorithms based on this. And so there's a slime mold algorithm. And this is ultimately, however you feel about this, why swarm intelligence is cool, because it has a slime mold algorithm, right? Everybody else is doing atoms optimizer and dumb name stuff like this. And we're, ant colonies, bee swarms, and slime mold. So it's got a cool effect. So you can actually use this algorithm in real-world logistics scenarios. And I'm going to show you an example where somebody designed an interstate system for America. These are major cities in America, population centers. They essentially put bread out. You can see the mold forms pathways to show you the most efficient type of interstate system. Pretty cool, right? Yeah, what other tech meetups doing slime mold stuff? I'm just letting you know, Pat Greenville's not doing stuff like this, they're just out having weird happen. There's probably people watching. If you're from Greenville, we love you. so, so this is giving an idea of like why these algorithms are interesting. The mold doesn't know what it's doing, right? It just knows that it's doing efficient energy. It's moving energy, in this case calories, around as efficiently as possible. And it really shows like it doesn't take a lot of work. It does it very efficiently. It finds really good solutions. And the same is true when we apply these into swarm intelligence algorithms. So where have these been used besides trying to plan interstate systems for our next run of that? Lots of places. So it's been used highly in robotics for trying to figure out things like cooperative construction, bridge building, house building, grouping dynamics, even coordination, so you see it in traffic systems. Scientific, so you've seen this. There are groups of people that use, especially PSO, across large data sets to try and find either groupings or how things are work together. There has been use, and this is, again, like kind of what my company does. It's been used a lot and pretty well studied for things like logistics, like shipping, supply chains, route planning, inventory management, all have been used, and it's related highly to kind of like what I do for it. And then increasingly, things like emerging areas, people are talking about it for like search and rescue, right? How do you coordinate a large search and rescue and efficiently do it based on terrain and other factors? And these are like areas that are still under active research. So if you're somebody who wants to, you can go on Google Scholar, and there are still guys publishing papers about swarm intelligence, even though this is largely, I would say, almost like, when we did a raise your hand thing, not a lot of people had heard about this. There have been robot swarms. Harvard built the kilobots, which is pretty friendly sounding. They built 1,024 bots that actually vibrate. So these things can vibrate and they can communicate by light. And they were able to move around and make like really complex shapes, all without having any central feedback. So very emergent tech. There was the Termes project, which was robots that actually could link together, and they were able to build things. So they would build like little buildings. And this is all, again, without a person being like, go here, put this thing here. They could give it goals, sort of like, oh, you'll feel better if you can get higher. And then the groups of robots would, based on just like, oh, I want to go higher, and I have a couple rules about how I coordinate with people, they would just start linking up and doing it. There was another project I don't know why I couldn't find it, but they actually were able to build like bridge building robots that were based a little bit on ants, and they were able to like go over water. Where another interesting thing that we're seeing this used for now, drones. If you have a drone swarm, how do you keep all the drones from flying into each other but still pretty coordinated? You can actually use boids, right? So it's always an obvious answer because that's how I like it. So the robotics was huge in real world applications. AntNet is essentially ACO. The British Telecom has used it for, actually used AntNet for trying to figure out traffic management for their telecom system. It's used in some ad hoc Wi-Fi networks. So, and then there's a couple other protocols that use it for hopping for like low-rad networks. So like if you go into these like networks that are designed to be deployed by the military or by like wilderness people that, are sort of ad hoc, there's protocols that. And routing, of course, has been used for logistics planning. Logistics and warehousing, ACO has been used for that. Automated guided vehicles, so if you go into some modern, there's a company actually here in South Carolina called Drobots that does a little bit of this, but there are actual warehouses where they have little robots moving around grabbing packages, and automated, Nephron has automated forklifts. Those actually use swarm algorithms to keep them from running into things they shouldn't run into. Southwest Airlines does their gate assignments using a swarm strategy. Supply chains, there's a couple of different supply chain companies. Telecommunications, IoT, frequency allocation. So when we have a bunch of frequencies, we have to figure out what's the best frequency to be on. I think originally there was a proposal for this to be used for mine. So for the actual, originally there was some talk about using it for how like 802.11 AC and onwards, there was some talk about when you were using different channels for your Wi-Fi, how we should allocate the channels. And there was some talk about using these and actually building them into the standard. I think that they ended up not doing that. But load balancing across servers, right? So you have a bunch of servers, they're geographically located in different areas. You have users that are from geographically different areas. You need to balance across them, and you want to minimize the amount of delay, right? But you also want to make sure that no system gets overloaded. So how do you route and load balance? There's some really cool systems that you can get online for load balancing servers. Finance. Basically, money, right? Ruins everything. So some people have used this for things like asset allocation. If you have thousands of assets, where should you put your money? How should you allocate it? What is the least risky option? Trading strategy optimization. So you can actually sit there. A lot of times what you'll have is like a general, if you're doing algorithmic trading, you'll have several algorithms running all the time and you'll have different parameters. It'll tune the parameters for your algorithm. And yeah, they've actually shown for PSO that largely creates better than human performance for asset management in financial portfolios. Environmental monitoring, it's been used for like things like wildfire monitoring, I think we mentioned search and rescue. It wasn't used, but we've used it as a case study for Fukushima. Was used as a case study where they actually showed one of the big problems with Fukushima is they couldn't get humans in. They tried to use robots. And that's actually become a big case study for like, well, maybe we need to develop better swarm robots that could go in and do things like search and rescue and help people out, because people couldn't go in there and they couldn't the robots couldn't communicate when they were in there, right? Because there was so much electromagnetic radiation and so much interference. So the idea is like, well, what if we had robots that didn't need to talk to anybody back home, but we could send like a team of them in there and they'd, of course, I'm imagining a horror show now of those like little yellow dog robots like running around and like dragging you, and you're like, no, I'm good here, and they're like, no, you're coming with us. But in general, it's a cool idea. So that's been used as a heavy case study, and post-disaster communications. Like I said at the beginning, each of these algorithms, they're not general. Like they apply better to different domains. So for optimization, ACO is best for discrete optimization. Particle swarm is kind of for continuous optimizations where you have like a continuous surface or numbers with low or no non-continuity. Like I said before, I've never used Firefly. Maybe it's great. I haven't tried it. I'm gonna have to try it at some point. ACO tends to find convergence really, really quickly, but it has a problem where it will find local convergence. It will settle into what we call local minimas and maximas really easily. PSO is more robust, but because you have to figure out where you drop all the particles in your big space, if you don't drop them well, sometimes they'll like cluster and group together and you'll miss all sorts of data. So this is what it means by sensitive to initial conditions. You can imagine that if I had a map with mountains on it, where I end up dropping these guys and getting them started has a real effect on how well they're capable of exploring the area. So now, because PSO is so efficient, what I usually do is I just like run it like 8 times, and I just like restart it with randoms each time, and that's my solution. I'm not saying it's a good one. ACO needs more tuning. PSO easier to implement. And actually, there are like problem matching guides, and you can get like a decision tree. So what you can do, and there's a ton of these, you can go out and you can actually pick different algorithms for different problems. There's a lot to consider, like how efficient they are, whether you need different, sometimes you can mix swarms with traditional AI. When should the swarm stop optimizing, right? Like if it's moving around, like when have you solved it? And what is the original input going to be, right? Like what are we going to give it as its first set of data? All of these are like the big questions that you have to ask yourself. Challenges and limitations. And we'll kind of start wrapping up here. Our theoretical understanding of these is not great. Like we understand little aspects, we know how the algorithms work, but we still don't really know like why ants are so good at building like really complex structures. We have some ways of mimicking it, but we don't understand every aspect of it. And how do we know this? Even with really high degrees of computational intensity, like even if I had a group of people, which are very advanced computers themselves, it would be difficult for me to coordinate some sort of swarm. I could do like little aspects of it, but if I took all of us and we tried to do the cookie experiment, None of us are allowed to like yell or. And I don't know how to tell you like, all right, you're only gonna do like your rule. Like I could give like a couple rules, it just wouldn't work. So something about this emergent behavior, we don't fundamentally understand. I will tell you that Gerardo Benny's theory around that related to the type of mathematics we use. I'm not going to go too deep into this because it's its own talk. That I don't think anybody would have fun at. He believed that the problem was, I'm really serious about this. That essentially we use two types of math in our world. We use discrete, like normal mathematics, like 1, 2, 3, we do multiplication, we add things together. That's the kind of math that we use in normal world. When we have really, really, really large systems, what do we use? Statistics, yeah, that's right. Good answer. So when we have very few things, we use kind of like deterministic discrete things. We have a ton of things, we use statistics, right? And so anything above, like you could say like 1 million, statistics is great. Anything below about 1,000, you could say you can still use pretty deterministic things. What if you have 10,000 things? It's kind of almost probabilistic, maybe, right? It's kind of almost deterministic. And so he was a firm believer that the answer was a branch of mathematics called cellular automata, where he believed that there were these simple rules. I'm not going to get into this too much, but he just believed that fundamentally you had to use this different branch of mathematics to describe intelligent systems, and that somewhere in there, okay, we're still here. Somewhere in there lies the secret. Now, I will tell you, for those of you who want to go home and learn about cellular automata, fascinating, incredibly visual, really easy to understand the basic concepts of. It's made by a physicist called Stephen Wolfram from the 80s, who's actually the guy who comes up with Wolfram Alpha and all the mathematical software. And what you should know about him is it's cool that he made all that money because he basically spent his whole life being crazy, drawing these little squares and studying cellular automata, which he believes are the fundamental universe secrets. And he has a book, great read, it's called A New Kind of Science. It's like 1,000 pages. It's half of its pictures. It goes on and on about how great these things are, and at the end of it, there doesn't have a solution for how it does anything. It's like, and I had to do it for a course in college, and at the end of it, I was like, what did we just do for 12 weeks here? It was like a bad joke. It was like a joke with no punchline, right? It was like, oh, we kept learning. You just kept feeling like, and tomorrow, well, I'm going to tell you how cellular automata fixes everything. And then it just never did. And, and the course is over. Thank you for coming to my TED Talk. Really, really frustrating. So if you want, it's fun to look at. Don't get lost. Stephen Wolfram already did. He's still crazy. Oh. Initial parameters are a challenge. It's hard to know. Sometimes you have to use heuristics to determine. So then you're kind of back to where you are with AI, which is you need some training data to know how to start these things. Large swarms, they have to communicate, and in certain networks, the communication is hard. Even though the computation for each one is easy, the bandwidth is limited, especially on computers, about how quickly you can move the data back and forth. No free lunch, which is to say that no single swarm solves all things. There is no general swarm algorithm that just kind of does everything. So sometimes you have to do a little trial and error. There's a ton. I'm just gonna highlight, people are still working on this. There's still robot guys that do this. There's still integration of stuff. So, and I'll tell you, our company kind of does AI swarm interaction. That's what I do at work at Collide, where we try and mix and match traditional AI and then use swarms to kind of optimize combinations of them. And that's how we do our logistics and our manufacturing optimizations. I looked it up on the internet. There's apparently a quantum swarm computer. I don't know about it. You can ask them over there. The quantum guys are there. They'll fill you in, I'm sure. I don't know anything about it. There is a cool thing, though, I will mention for human swarm interaction. So again, that comes back to the question of there's still an open area of research of could you even build a human swarm? And could we have emergent behavior without anybody being knowing the answer to the problem we're trying to solve? And what would that look like? And there's people that research this. If you want to play with this, there are open source libraries. Like I said, these will run on virtually any computer. So you can build these up. There's some great books. Swarm intelligence from natural artificial by Eric Mondo is the basically like the book, right? Like if you're getting started, read that one. It's a really good book. And there's courses about it. There's tons of GitHubs. There's cool visualizations where you can like swarm things together. So I highly recommend if you're interested. There's really no limitation to how much like free cool stuff there is out there for you to try this out. I'll wrap this up by just saying, like I said, my whole thing originally when I went to college was emergent intelligence. This is what I was really interested in. How does something just become smart? Because I think it's a question that we don't understand as humans, right? There's some collection of cells that we're all sort of these just like electrified skeletons, and somehow we're smarter than other electrified skeletons. Why, right? And I think fundamentally we don't really know, right? And I think that's a huge, interesting question. And the fact that we can see, there's something that makes things that are alive different than things that are not, animate, inanimate. What is that? Like, when does that happen? And this is debated. Like, does it come from simplicity? Does it come from complexity? Is it because there's some complex interaction within living things that makes them smart, or is it actually some very simple thing that we just happen to have? There's a whole field of study called artificial life that I nerd out on. There are journals about this. I applied to one last year. I did not get my paper accepted. It wasn't that great, but I mean, I really want to go to Japan to try and answer this. So when we look at these, I find this, not only is this an area that I do, like I said, actively for like the work I do, and the work I've done in the past, but it's like this huge philosophical thing that I spend like lots of time sitting down with people and having coffee and being like, why does like smart happen? And then, I don't know, then we drink more coffee and we move on with our lives. But it's kind of like my favorite thing to do, and I hope that this talk has to an extent inspired you to like have that same question. Like, why are ants smart? How smart are they? Like, why can ants do things that I can't do? What would it take? Like, and yeah, okay, that's it. I think it's really cool. Thank you for coming. Questions and answers. Well, there can be questions. I'll do my best on answers. That's it, guys. That's what I got for you. What do you have? Questions? Things you want to know? Yeah, you can clap if you want. Thank you. It's always cool if you have to ask. Are there any questions? Cool thoughts, comments? I'm sorry, I kind of sped through that. I wanted to try and end at 7:30 like we're supposed to. Yeah, I mean, so what is I think the interesting aspect is less about how we apply a certain algorithm and more about how Collide has an ethos, right? So my company, Collide Technology, what I realized being a data scientist for many years was that dealing with data scientists was always really frustrating because you have a problem and what you want to do, what you have to do is you go to the data scientist and then we always want two things. We want like a lot of money and we want like a lot of data, and then we're like, okay, give us all these things. We'll come back to you in 6 months and a year and maybe you'll have a solution. And it's really a requirement. It was a frustrating thing for me. Almost every project that I worked on as a data scientist, there wasn't enough data. We wanted more data. We were creating synthetic data. And so I had a lot of talks of thinking about, okay, the problems that we're trying to solve a lot of times in like the real world, in things like factories where I want it to have like a big impact, logistics, planning, how much data will we need? And because I had this background in swarm intelligence, I really kind of came to the conclusion, I was like, what if we could provide, maybe not the best value, like maybe there's like ways that you have all this data that you can provide better value. But what if we could provide some value very quickly to people at a very low cost so they can see it, and then we could use that to leverage building better and better things as we get more and more data. So what I realized is like, you go into so many places as a company, and you're like, well, what are you doing with AI? Like, nothing. What are you doing with data? Nothing. And then like, your solution as a data scientist is like, let's build an LLM, right? And like, let's do all this stuff. And it's, well, then we got to get all this stuff together and it costs a lot of money. And like, I wanted to build something where we could show value very quickly, and we could solve problems. Like, I think a lot of AI is focused on prediction. I mean, it's almost all focused on prediction, right? Whether it's predicting the next word, whether it's predicting like what something will be, depending on inputs. So it's all pattern recognition and prediction, but in a lot of cases, that just tells you more about your problem. So it's like cool to know, like I predict your sales will go up 10% next month, but I was just example, well, what if I want it to be 15, right? That's an optimization problem. So I wanted to solve two things when I started Collide. I wanted us to give solutions, and I wanted those solutions to be helpful, like to optimize and make things better. And I wanted us to be able to provide value very, very quick. And that's really like a really nice convergence of Swarm, right? It's like we can go into very low data environments, and then we're able to provide value very quickly, very inexpensively, and then build trust and relationships with clients without having them give us a lot of resources. And that's what I wanted to build, and that's kind of what we have built. And to give you an example of kind of the stuff we do, things like scheduling. You have a ton of resources, you need to figure out how to allocate them across a bunch of different parts of a factory. And what we'll do is we'll use a Swarm algorithm to like tell you what the ideal way to schedule all your employees, all your machines, and all your materials across the factory. We can usually do this in like a few seconds. So it's like incredibly lightweight, doesn't require expensive GPU time. A lot of times it doesn't even require that we have a lot of data. We just need to know like what resources are available, like what people, what machines, what jobs need to be done. And we can do like a pretty straightforward scheduling algorithm from that. And that's like such a fundamental problem at so many places. Scheduling resources, scheduling events, scheduling time, scheduling issues that need to be done. And so we really focus on that. And I don't know, I'm very passionate about it because I think it's a really cool way to think about the world. I think it's a really cool way to try and attack the problem. And I think it's a little unique. At least for me, I think we're kind of unique as an AI company that we have that part. While we still do deep learning and we still have like LLMs and stuff in the mix, I think it's cool that we have this like one thing that other people don't really, a lot of people don't really use. And so that makes me happy. Go ahead.
So I have a question. I think you touched on it a little bit, but like, what's like the big difference between traditional AI and swarm intelligence, like in terms of like using like the pheromone trail example?
Sure.
Yeah. What happens like when I guess ants lose like they lose I guess like the pheromone trail a little bit, and they end up getting lost, and they're just like completely lost off the path. Like in terms of like recovery, how do they recover?
Yeah, they die. Right? No part of your swarm is important. So you create like a boundary condition, and you go, oh, these ants have just gone off the map.
Yeah.
Gone. Like I know that's like a really cruel way to look at it because like no individual part of your swarm is important, including whether in the real world or the digital ones. Oops, right? Like, oh, some of the ants wandered off, or they're just dead now. But no single ant mattered to the collective, right? In fact, no single 1,000 ants really matters to the collective. And that gives you an idea of the robustness. And the same thing digitally, just, like this part of our swarm is like gone, just whatever, delete those and put some new ones down.
So is it the same concept with traditional AI? Because I know that you said it relies on like the centralized unit.
Well, when you normally have let's say, again, I'm also oversimplifying. When I say traditional AI, let's kind of narrow that down to, I mean neural networks, right? Because forests and suppose vector machines, and there's all this other stuff, right? So so let's like limit the discussion to sort of a neural network. A neural network is like one giant matrix, a series of matrix calculations, right? And you can't really easily pull them apart. There is pruning, but you do that afterwards, right? So you have to have all of these things running together with the different weights to get the answer. If you start literally pulling vectors out of it, and actually they've done studies on this, it'll like lose the train of thought. And in fact, in the case of LLMs, it'll actually exhibit signs of schizophrenia. So there's some really cool studies on that. But essentially it acts as one big unit. And that's why like if you want to run like an LLM, it's like 200 gigabytes. Because it needs, the LLM or the neural network, it has a memory. It remembers all this history of the stuff it's doing in its own way, right? The swarm doesn't. Right? The swarm doesn't have to remember anything. It's got 3 or 4 rules that it follows and just does them. And so it's so much more efficient. Whereas like if you start pulling apart, just like in a person, you start deleting memories from a person, like who they are, how they act, what they do, changes. right? We see this in brain damage victims and stuff, where they get traumatic brain injuries, where some part of the brain is damaged, and the brain is in some ways very decentralized. It has all these neurons that can recover, but if you start losing aspects of that, it falls apart. Whereas what we just talked about before, I don't know, if I stomp on like 10,000 ants, they'd still be ants, just keep doing ant stuff. And that's like a really resilient thing. But there is no heuristic. And I will say, obviously Gerardo Benny did not crack it, right? He has a really good definition for what intelligent systems are, and he has this whole cellular automata thing. I buy into all of it, right? It's like, I just sit up at night and be like, this guy's smart. I will say that in my opinion, the part that we were missing was heuristics, was that there is an aspect of history and memory, maybe very short term, that I thought would play a crucial role in the philosophy of what it means to be intelligent, personally. And this is one of the reasons that some of the research I did on magnetic systems was so important, because I believe magnetic systems inherently have a memory.
But magnets do have a type of memory, right?
Right, they're heuristic. They have a hysteresis, right? So I believed that if you built an emergent system based on magnets, that you would get intelligence would just happen.
But I guess with the unpredictability of the swarm, magnets I feel have a much more stabilized predictability, whereas the swarm, the whole nature of the swarm, centuries. People have been studying the ants for centuries, and they still haven't figured out how the ants are able to do all this except through pheromones. Like that's it. The unpredictability of that. Whereas with artificial intelligence, although we feel it's very black box, you can stick it in a test environment and it recreates within the production environment. However, with a swarm mentality, how are you able to predict that what occurs within the test environment is also going to be what occurs within the production environment?
You can run a lot of iterations because they're cheap, so it becomes probabilistic. But yeah, actually, you don't know. And we don't typically because we're using it for optimization, right? You're pulling levers on something else. So you're basically saying oh, I have this, and these are the only levers I'm going to pull, and it's a pretty constrained environment, right? For me, if it if for our stuff, if it went crazy and was I don't know, jack the pressure on this machine up to 100,000 psi. We have safety stuff in place. Don't do that. Okay. This one's bad, right? Kill that ant. Next one, please. Yeah, it doesn't have the same thing. But again, in the case of AI, you're usually using it in a system where you know the answer. You're trying to get it usually to replicate things people do. Dog, cat, dog, cat. We keep showing it these things. A person can do that really well. But if you went into again, a lot of what I say I do for work is I try and solve problems that people and AI are bad at. Let's say I turn all the lights off in this room and I said, we all have to get out of this room safely and as quickly as possible. Disaster, right? We're bad at that sort of thing because we would have to feel around. We wouldn't have any rules. We'd be out here playing Marco, hold on, Marco. And we could try and solve it, and we probably would eventually, right? We probably all eventually. But if you said that be efficient? No. But you could get dumb ant pheromone trail thing maybe to do it, right? And they do it, like I said, they have used it for planning search and rescue operations. So again, I think it's a lot of what we use at AI because it's based on Hebbian learning, which is the biological structure that humans learn off of for neurons. It does things to an extent that humans are good at. The stuff that I'm worried about is what are all these problems that people are already bad at? So for example, for us, we're trying to do a lot of scheduling at factories. How do you schedule a factory? There's 3 people with a whiteboard and 500 post-it notes, and they do this every week, and it's a disaster. It's never optimal. That's not a thing that we figured out. Whereas when you say oh, I want to train an AI that can inspect car parts, I can get a person to do that. I'd be look, this one's good, this one's bad. You got it? Yeah, okay, cool. If you see anything that doesn't look like this, ring the bell. And yeah, there's some value in people not having to do that anymore, but in my opinion, that's there is a solution to that problem. Maybe it's not the best solution, maybe it's not the most cost effective, but the solution exists. But in the world of scheduling, where you're trying to schedule a lot of things, holistically across different aspects, that's not a solved problem. And so the fact that we can we've developed software that allows us to do it, to me, I think is really cool. because it actually brings a new kind of value into your environment. Whereas theoretically, most of the stuff that other AI is doing, you had the value, just maybe didn't have it as efficiently or as cost effectively or as consistently as you wanted. But you had it, right? Because people were doing it. That's my opinion, right? But you're right. There are some limitations. And you can't solve all the same problems with these two things. They're fundamentally different. Dana, I think, did you have a question?
This was very accessible. I really appreciate
Okay.
it. I like the concrete examples. Can you talk about the Southwest Airlines? How do they use swarm?
They use it to schedule gates. So what they do is they say that their metric is like, what gate should they put a plane at so that people have to travel the least amount of distance? So it's both a time minimization and a route planning problem. Are they doing it, crushing it? I don't know, but it was better. I think I saw that it's like 30% shorter routes or something that Southwest uses or something. I have thrown my name in the hat at a couple of airlines and be like, hey guys, I mean, like United, I just got off this and I don't know how you did it, but I bet I could do a better job if somebody wants to call me. I'm just saying, I don't feel I can do a lot worse. Like, still can't find my bag. So I think there's a lot of problems out there that, again, like it comes up to like as these systems get big, they get really hard. And then it's hard to tell if they're just inefficient or just highly disruptive, right? A big problem with things like airlines is just like weather. I mean, I have a pilot's license, and what I can tell you is that flying is the least efficient form of travel ever invented, right? Like, I'm always, like, every time I try to fly anywhere, I'd be late 6 hours, like, I'd show up like a day and a half late. I once had to fly back from Charleston to Newberry. I was a day late because the lights didn't work at the airport, and so I couldn't fly back, like, because I couldn't have anywhere to land. Like, I was like, what are we doing here, guys? Like it's expensive. It's not even that fast in comparison when you're using a small airplane. It's a nightmare, right? So now I go to these airlines and I'm a little bit more forgiving. Like the fact that it works at all to me is sort of like shocking. Because like when I fly like little airplanes, like just late. I was 5 hours late for Thanksgiving at my house, and I flew a little airplane because I just got my pilot's license. And my dad and my uncle are pilots, and they were just sitting there like, well, we knew you were gonna be late. Planes, what are you gonna do? They're fun, but they're not great. So I think that's the other thing is like we have these highly disruptive systems, but I do think that's where a swarm becomes a really good idea. One of the things we point out is that like our schedulers are super efficient. Like generally we can schedule like a whole factory in a few seconds, which means that when the intern throws a wrench into the machine and it blows up, and you need to reschedule the factory, you just click a button. You say, this machine's down, it's gonna be down forever. What should we do? What's the most optimal? And so like, what we sort of advertise is not always that we're the best, but that we're easily the most dynamic, right? Something goes down, and in fact, if it's got automated machine queues, like it'll start rescheduling it as soon as that machine comes offline. So again, I think right time and place, and there's a lot of problems. Don't get me wrong, I still do a lot of traditional AI work, and there's some problems that it does really well at. On pattern matching and stuff, like there's some papers of research about like swarm. Like it's just trying really, really hard. Like those are purely academic things. Like, oh, we pattern match with an ant. Like why? Like, what is it? I mean, I guess you always hope that maybe you find out it's really good at it, but it's usually not. Other questions?
Right.
Anybody?
Right.
Anybody?
Right.
Nobody?
Me. So, other than what Collide does, what's the coolest sort of application you've seen these swarm things for?
Oh, robots.
Robots?
Like,
Yeah.
the little like bridge building robot. It's insane. Like, I mean, I don't know which grad student got stuck with the job of building like 1,000 little robots, but how cool. Like, I don't know. To me, like, I'm usually pretty down on robotics. For those of you who don't know me, I like worked at robotics. And just to me, it always seems like a really obvious thing. Like, oh, you're gonna build a hand and it's gonna move it over here. So people are always solving these like robotics problems that I think are dumb. This is not one of them. Like people are like, we're building 1,000 robot butterflies and they're gonna fly. I'm like, this is the coolest ever. Like what? Like this is what you go to grad school for. I don't know if that'll be useful for anything, but dope. So to me personally, that is probably the coolest. That's always to me the cool stuff. It's like these physical implementations when guys get these drone swarms with the weights algorithms. They don't hit each other. And they're flying around super fast. I think that's the coolest stuff. I don't think I had anything really cool there, like pretty obvious, like killer robot swarms.
Well, I don't think people know how, about that as much. I think,
Well,
yeah,
like
we see it all the time. We don't know.
my whole thing, and where I find this really interesting, is that there are emergent properties in nature that even before you get into biological systems, magnetic systems, they emerge. Like if you have groups of them, they will group together, they will form certain patterns based on a lot of like physics. And there was a whole field of study when I first was going into nanotechnology. It was all about these ground up approaches. They were all entirely emergent. This idea that like, if you just mix these right things together, this stuff would just grow, right? And then we'd have these structures that would just emerge, right? And some of them did. Like people got like the right chemistry where like a wall would just grow. Or carbon nanotubes are arguably what we call self-assembled systems, right? You kind of like create this layer and then you add the right gases and pressures together and then like fields of carbon nanotubes grow sometimes, if you get it right. And like, a lot of those, you can get these very highly deterministic structures, but then you can start seeing when you get into like closer to biology, but not quite living things like DNA that have these natural helical structures. Like, why does it do that? Why does it bond? Why isn't it like a straight line? It's because it's a very energy efficient package. But it's, your DNA is essentially a binary system, right? It's just two different pairs of things. It's a computer. And the fact that emerges inherently by itself. You get into things like protein structures. Again, not technically alive yet, but enzymes. And we've seen like wheels that spin in things that look like bearing structures. They just pop out of like the structures of living things. And so I think all the way from the physics, all the way up to like where you get into the stuff we work on with like swarm intelligence, any of these self-assembled emergent systems, I think is fascinating. It's like what creates, if you have any sort of physical structure, it's just essentially a cloud of chaos. And from that chaos, you get like this negative entropic sort of system that order emerges. That's not intuitive. Like the order would emerge from chaotic systems. I find that fascinating. It's the kind of stuff that made me want to just like get a PhD and just sit around and like spend government money for like 40 years. Just be one of those heroes. Just crank through American tax dollars and, publish papers. That's what I wanted to do for a long time. I still kind of do. Other questions? Nothing? All right. Thank you all for coming to the swamp. You guys have been wonderful. I'll be here all week. Take your waitresses. Thank you very much.
That was great.
I hope that was fun, guys. I know I kind of rambled a little bit. But...
That was fun. I have the Jeep book. I think I have the particle swarm optimization.
Yeah, there's a bunch. Like a lot of people got them back in the day.
Jeep's on the bookshelf, I think, in their office right now. Yeah, I've forgotten about all that stuff. Yeah, I did all that research before I got an LCN.